Okay, so I'd like to thank the organizers for the opportunity to talk at this conference. And as you see, my title is Topological Free Entropy. So this is the notation for the topological free entropy. And the idea is to replace in the definition of the microstates free entropy to replace the matricial microstates by microstates where the distribution is replaced, the moments are replaced by norms, so norm microstate. So this idea comes from two sources. One is what happens in topology in dynamics, where you have the dynamical entropy, but if you have automorphism of metrics, compact metric space, then there is also a topological entropy, and you have the relation between the topological entropy and the Kolmogorov-Sinai entropy, in that the topological entropy turns out to be the supremum over the Kolmogorov-Sinai entropies with respect to all invariant probability measures. So that's one source of idea. And the other is that the work on random matrices has this type of strengthening the results about largest eigenvalues of random matrices, which are, of course, more difficult and stronger than the results about limit distributions. And at the moment, this is some older work of mine. At that moment, there was a breakthrough of Hagerup and Thorbjørnsen, who gave a sweeping generalization of the results about the largest eigenvalue for random matrices, almost sure convergence of the largest eigenvalue, which is the norm in the case of certain Hermitian random matrices. And what's happening nowadays is that there is much more work of this stronger type. There is work about, you hear, strong asymptotic freeness, strong convergence to the limit distribution. There is a wealth of new results. This and so one can hope that some of the examples to which these things about topological free entropy applied can be now probably extended due to these new results. So there is one other thing, is that this topological free entropy is a C-star algebraic quantity, and that's why it's called topological versus what would be measurable. And there is all this trend of moving things from von Neumann algebras to C-star algebras, like you can see with ideas of subfactor theory and other things, which are moving towards becoming C-star algebraic notions. So this is also has to do with the movement of moving the entropy from von Neumann algebras to C-star algebras. Here is this older paper of mine in Letters in Mathematical Physics, where I introduced this topological free entropy. So let me start by recalling what the microstates free entropy is. I'm having a von Neumann algebra. Having a von Neumann algebra M with a trace state, and I'm having an n-tuple of self-adjoint elements, which you view then as non-commutative random variables. And then you have the space of microstates, gamma x1, xn, mk, epsilon, which are the match. So okay, so you have here these parameters. Epsilon is the degree of approximation. M is up to what order of moments one goes in describing the distribution. And K is the size of matrices. So if I have x1, xn like that, then I'm looking for matrices A1 and AN, K by K self-adjoint matrices, such that the moments, these are moments up to degree m, so I'm this product of the variables up p tuples with p less than or equal m, is within epsilon of the corresponding moments for the AIs with respect to the normalized trace on the matrices. And then what one does, one takes the logarithm of the volume of this space of microstates, one divides by k squared because one has matrices, and one adds this correction n over 2 logarithm of k that has to do with the volume of the ball. And then one does infimum over epsilon positive, infimum over m, and one gets the quantity which is free entropy, the microstates free entropy. So what one does is when one looks at the topological free entropy, one replaces the space of microstates by norm microstates. So you have here chi topological A1, AN. Now the variables are an n-tuple of elements in a unital C-star algebra. And instead of moments, you have to look at polynomials, P1, Pm. You could have replaced also in the definition of the microstates free entropy. You could have taken, instead of moments, taken expectations of certain polynomials. So here one takes polynomials P1, Pm, has A1, AN, one has again K is the size of matrices, epsilon degree of approximation. But instead of moments, one looks now at P1, Pm polynomials, and instead of expectation, one looks at the norms. So one has these norms of Pj, C1, Cn. C1, Cn are the matrices in the microstates, minus Pj, A1, An, the norm. This would be within epsilon one from the other. Now, it is tempting to think in such a situation that you might introduce instead of these polynomials to look at matrix-valued polynomials. That is, yeah. So instead of taking a polynomial in C1, Cn, you would take a matrix with entries polynomials in C1, Cn, and you take the difference of the norms of the matrices. Well, the passage to matrices actually does not contribute anything to the quantity one obtains. The quantity one obtains is the same if you replace polynomials by matrix-valued polynomials. It's in essence because the norm on a C-star algebra determines completely the norm on the n by n matrix. It's a bit more tricky if you write it down, but that's in essence. So then one plays the same game. One takes the lim sup, k goes to infinity, k 1 over k squared, logarithm volume of this microstate, of this norm microstates, and again plus n over 2 log k. And then again, infimum over all these parameters which determines the type of microstates. That is, one takes the infimum over m tuples with m increasing of polynomials and epsilon positive. And one has a few properties which are similar to those of the microstates free entropy, namely, one of them is that the topological free entropy is subadditive. Yeah? If I take A1 AN and B1 BN, then it is less than or equal the free entropy for the A's plus the free entropy, the topological free entropy for the B's. And then you have upper semi-continuity. If you have, so you take A1, AN, self-adjoint elements in your C-star algebra, and then you have a sequence of such n tuples of self-adjoint elements in the C-star algebra, which converge in norm distribution. Convergence in norm distribution will mean that the norms of any polynomials in A1, AN, P converges to the norm of A1, AN. And then what happens is that the lim sup of the topological free entropies is less than or equal the lim sup of the, is less than or equal the topological free entropy of A1, AN. So this is upper semi-continuity of the topological free entropy. Then there is the change of variable formula. The change of variable formula for the microstates free entropy is with a Cadison-Fugler determinant of a certain Jacobian. Well, here you have to take the norm of the Jacobian, because you are working with norm microstates. So you have the topological free entropy of functions of A1, AN up to functions of A1, AN, F1, Fn. These are functions. What do I mean by that? They are given by non-commutative power series in n variables. And you have the additional condition that these power series should have inverses which have lots of nice convergence properties. That is, in essence, it's a version in n variables, non-commuting variables of what you would say. You have an inverse, and the inverse is defined on a neighborhood of the disk or whatever. Yeah. So then you have this type of formula with topological free entropy of F1 of the functions is less than or equal to the topological free entropy plus n times the logarithm of the norm of the Cadison-Fugler determinant, the norm of the Jacobian with respect to free difference quotients. Now, there is a competing quantity. So remember, if you work with dynamical entropy, you have that the dynamical entropy of the topological dynamical entropy of an automorphism of metric space will be equal to the supremum of the Kolmogorov-Sinai entropies of the automorphism with respect to the invariant probability measures. And so one has an equality of two quantities, and it is natural, therefore, also here in this situation to look at the corresponding quantity, which is the supremum of the usual microstates entropies. Yeah, here is the supremum of the microstates entropy with respect to all the trace states of the algebra A. And of course, if one has all the interest not to take a too large C-star algebra, so one will assume that A1, AN is a generator of A. So one defines then the free capacity, which is the supremum of the microstates free entropies of A1, AN when you take the representations in the von Neumann algebras determined by the trace states tau. Yeah, so you take a trace state tau, you do Gelfand-Naimark-Siegel, you get an n-tuple of elements in a von Neumann algebra with a tracial state, and you have entropy. And then you take the supremum of all these. And this quantity is subadditive also like the topological free entropy, like the microstates free entropy, it's subadditive. And the change of variables formula has a certain more precise form than the one I stated for the topological free entropy. Namely, you see here, instead of taking logarithm of norms of the differential of f1, fn, the change of variable, one takes the Cadison-Fugglede determinant, this logarithm of the determinant. It is that's the Cadison-Fugglede determinant of the change of variable, and it's the supremum over all trace states. So it's a more precise formula. And one of the things which justifies this name of capacity is that if we look at what happens in the case n equal 1, so if you have just one self-adjoint element in a commutative C-star algebra, so it's C-star algebra, the continuous functions over the spectrum of A, then a trace state is the same thing as the probability measure on the spectrum, and you have the free entropy for one variable, which is a certain constant, theta is something with the logarithm of 2 pi, etc. And here it's plus the logarithm of s minus t d mu s d mu t, which is minus the logarithmic capacity, minus the logarithmic energy of the measure mu. So the capacity is comes from this minus logarithmic energy, but it's the extremal, the measure which will be extremal with respect to this. This is the equilibrium measure. So what one does in potential theory is that actually one takes also an exponential of this whole thing. So one takes exponential of k of a minus theta and calls it the logarithmic capacity, but it's the same information. I mean, the fact that you take the exponential in potential theory is motivated by the fact, by other properties, which make it natural to look at the exponential. Yeah. So the problem, one of the big problems here is what happens with this equality, which you have for the dynamical entropies. The dynamical entropies, you have this supremum of Kolmogorov-Sinai entropies is equal to the topological free entropy and topological dynamical entropy. And one has to wonder whether something so the big problem is when is this free capacity equal to the topological free entropy of A1AN. What one would like is, of course, to be sweeping to have something of this generality, but one would like at least to know more and more situations when some equality of this type holds. Now, there is a nice feature, is that at least half of the answer is quite general. I don't know about the other half, but one half is true. So you have an inequality. The topological free entropy of you see the topological free entropy of A1 AN is less than or equal the capacity K, the free capacity of A1 AN. It is interesting here to notice the following thing. You see in the right-hand side, these microstates with which one works are defined only by norms. So there are no things about the distribution in the right-hand side. You have K of, excuse me, no, it's the opposite. What? No. So here, what you have, excuse me, on the left-hand side, you have the topological free entropy. And the topological free entropy is with microstates which are given only by norms. Whereas on the right-hand side, you have this supremum of entropies, which are microstates entropies, which are defined by distributions, so by expectations of the expectations of monomials, expectations of polynomials. And still, though you have here on the left-hand side, you have only norms which you control. On the right-hand side, you control distributions, you control expectations, and you have still this inequality. So it's not like writing like being an obvious thing that some norm microstates are included in the other. You have to work a little more to get this inequality. But the harder thing and the unknown is the opposite inequality. And at the time when I wrote that little note, it was quite fortunate that there was a work of Thorbjørnsen and Hagerup, which made it possible to have some non-trivial cases of equalities. And one of the cases of equalities is the semicircular case. So I'm having a C-star algebra generated by a semicircular system. And then the topological free entropy of S1 Sn, the one defined with the norm microstates, is equal to the supremum of this free microstates free entropies for S1 Sn. But here you have the supremum is just one element because the C-star algebra has a unique trace state. And it is this microstates free entropy of S1 Sn. But yes, a semicircular system. They are freely independent. And the essential ingredient is the Hagerup-Thorbjørnsen theorem, which guarantees that you have polynomials in Hermitian Gaussian random matrices which are independent, ID, etc. Converge almost surely the norms converge to the norm of the polynomial in the semicircular system. And there is a lot of work to generalize this Hagerup-Thorbjørnsen results. So there is work of Capitaine, Donati Martin, Mal, Collins, Bordenave, and there is more work. There is now also work by Buddy Harjo, work by Michael McGee and co-workers, etc. There is a lot of more work, and which gives hope that one can get more general results of this type, in more situations where to have equalities. There is another situation about the universal n-tuple of Hermitian contractions. So if I take the C-star algebra, this is a universal C-star algebra for an n-tuple of contractions. So it is a C-star algebra which is a full free product of continuous functions on -1, 1. By contractions, I mean Hermitian contractions, self-adjoint contractions. Yeah, so this is the C-star algebra, and T1, Tn are the generators for each of these elements. Then you have again equality of the topological free entropy of T1, Tn, and the free capacity. And one may wonder when the maximum is attained. And the nice thing here is that it's a situation where things don't occur with a semicircular distribution. One has here an arc sign measure because in classical potential theory, the arc sign measure is the equilibrium measure for the interval -1, 1. So if you take the free product of equilibrium measures, of these arc sign measures, yeah, this is an arc sign distribution, 1 over pi, 1 minus x squared, minus 1/2. It's 1 over what you have for the semicircular measure. Then for this, the equality is attained. And you have a general notion of what would be a free equilibrium trace state. So it is a trace state where the microstates free entropy, you see microstates free entropy, chi of A1 tau, AN tau, is equal to the capacity, is equal to the maximum over this. That is a free equilibrium trace state. Now what happens, that's such a trace. Now such an equilibrium trace state exists always. But the difference from the classical potential theory, you have only one equilibrium trace state, or one equilibrium measure. Here, there could be more. It's not said that it's unique, yeah? But there exists one. It's easy to see that there exists one. And I should say that in my little note, I'm looking for the more complicated quantity where I have also these variables A1, AN, and B1, BM, and everything in the presence, A1, AN in the presence of B1, BM. So the microstates are obtained from microstates of the N plus M tuple A1, AN, B1, BM, and their projections to microstates in A1, AN. There is another notion here, which is a semi-microstates quantity. So instead of looking, when one takes the microstates and defines also the topological free entropy, etc., instead of having these norms of polynomials being within epsilon, one can require only to have an inequality. So the norm of P polynomial in C1, Cn, the matrices, is less than the polynomial in A1, AN, these elements in the C-star algebra plus epsilon. So one has only half of the condition. Now, when one requires only half of the condition, actually, under quite general situations, you're going to see one has to make a very small extra requirement, and it boils down to the same thing. So in general, you have that the topological with semi-microstate topological 1/2 is larger than or equal the chi topological. But if the norm analog of the conjecture holds for A1, AN, this is what is called MF, A1, AN generate an MF algebra in the Blackadder-Kirchberg sense. Then you have actually equality. So the fact that you take microstates only with inequality, one-sided inequality, that does not increase microstate space so much that you get a larger quantity. You get still, it's a simple trick. But this is also what makes it possible. For instance, if you would wonder for some of these groups considered by Michael McGee, where he proves something which is stronger than existence of microstates for the generator of the group generator for the reduced C-star algebra. Then by having such, if you would like to compute the topological free entropy in that situation, well, I mean, you can have a little help from this because it's enough to look at half microstates, that is, to look at having only the inequality. But the problem is still quite hard to go further. Okay. Now there is another quantity, which is topological free entropy dimension, which is essential to the hope of having for Neumann algebra applications of free entropy theory. So the free entropy dimension, which is denoted delta x1 xn, I defined it initially as a Minkowski content quantity derived from the microstates free entropy, but later Kenley-Jung found a direct equivalent definition based on epsilon nets, which is more convenient also in this context to use for defining a topological quantity. It's better. So I'm using the definition of Kenley-Jung here. So remember this: if X is a metric space and n epsilon X is a minimum metric, it will have here, can take it compact. Metric space, and the minimum number of points in an epsilon net of X, you know this n epsilon X, and then you can take the epsilon A1 AN lim sup 1 over k squared, and so instead of the volume, you take this logarithm of this n epsilon of this number of points. Then you get a quantity, you put inf m, inf, etc., and then you get the topological free entropy dimension. Delta top A1 AN is a lim sup, epsilon goes to 0, the epsilon A1 AN over absolute value of logarithm epsilon. Yeah, I mean, if you look at the papers of Kenley-Jung, there is epsilon nets covering, etc., but these numbers are so trivially related one to the other that they give the same quantity. Yeah, and there is, of course, the competing quantity, like we did the capacity quantity. You have free entropy dimension capacity, and you take the supremum, and here you put this modified free entropy dimension. It's again, you put something in the presence of something, but let's not go into this. It's a variant of the free entropy dimensions for tau, the trace states of A. And then what happens is that, for instance, if you have the topological free entropy is not minus infinity, then you have that the delta top, the topological free entropy dimension is n, and you have that the topological free entropy of a semicircular, the topological free entropy dimension of a semicircular system is equal to the topological free entropy dimension of this universal n-tuple of self-adjoint contractions, is equal to the capacity, the free entropy dimension capacity of S1Sn, and free entropy capacity of T1 Tn, and is equal to n. So all these examples you have equality, but of course one would like, I mean, now that there is so much progress with strong convergences and asymptotic freeness, etc., strong asymptotic freeness, all this stuff, one would like to have, if possible, more general situations. So here are, again, the big questions. By big, I mean quite general questions. So it's first of all if this free entropy dimension capacity is equal to the topological free entropy dimension. When do we have equalities? And when is this delta topological A1 AN independent of the choice of Hermitian generators? Now you know that for the free entropy dimension, there is all this work of Kenley-Jung, and then further things about it. The strong one-bounded C-star algebras, Kenley-Jung, Dimash-Lachtenko, and Ben Hayes, and it's all these things based on norm microstates. And one can ask whether there is something similar. There is a similar things of like one-bounded C-star algebra, strongly one-bounded C-star algebra, strongly one-bounded entropy, etc. Now here the answer, the situation is the following about this question. So this is really a quite natural question, what one can do about the strongly one-bounded stuff in the topological setting. It is possible that there is already relevant work in this direction. Namely, there is a work of Don Hadwin and Junhao Shen, which gives results about certain C-star algebras where the topological free entropy dimension is independent of the chosen generators. And so this may be, the problem is that he talks in a different language. I mean, it doesn't use the strong one-bounded terminology of they. I mean, it's both somehow again and on Haydn. They don't talk in terms of one-bounded, strongly one-bounded, etc. But it is possible that their work contains already relevant things about this question, this second question. What is the topological analog of the strongly one-bounded stuff? And here I'm going to give you a few things from Don Hadwin's work and Junhao Shen. They have much more general results. Their results refer to, I'm going here to say only things about finite dimensional C-star algebras. They have for more general algebras, when they put conditions, certain quasi-diagonality type conditions, certain conditions, MF. I should notice also that in the Elliott program, there begin to appear things about MF algebras, work of Kristin Courtney and Wilhelm Winter. So maybe someday also this topological free entropy will be suitable to do certain things on MF C-star algebras satisfying I don't know how many conditions. So here is a very primitive way of stating the simplest results of Don Hadwin and Junhao Shen without going for generality. So what they prove is that if AN is any generator of a finite dimensional C-star algebra A, then the topological free entropy, when the topological free entropy dimension delta top A1 AN is equal to 1 minus 1 over the dimension of A. So it is not only that it's independent, but it has also a nice formula. You realize that if you have generalizations of these results for infinite dimensional C-star algebras, then you have exactly results that the free entropy dimension is 1, like the strong one-boundedness results where you have free entropy dimension 1, things like that. The other result I would like to mention is that if you have AI's commutative C-star algebras, continuous functions on some compact set Ki, and Ki compact sets contained in the real line, and Xi are identical, the identical functions, the coordinate functions on Ki, then if you take A1, AN, the full free product of A1, AN, then the topological free entropy dimension of X1, Xn is equal n minus the sum 1 over the cardinality of the Ki's. That's another result. And they have also other results like on the free entropy dimension. Here you have two algebras, A and B, and you take the direct sum, and to take the n tuple, which is A1, B1, direct sum A and direct sum Bn. What's interesting here is that they have that this is the maximum of the two in case the free entropy dimensions are topological free entropy dimensions are equal to 1. But if the topological free entropy dimensions are under 1, then this is no longer so. They have a quite nice formula, which is more complicated. It's not the maximum, and it's an exact formula. It's not an inequality, and it gives you what the topological free entropy dimension of these sums A1. It's something like a fraction, I don't know, T plus A, something divided by something like that. And there are more general things that I would have to introduce for this, all these MF nuclearity things and certain types of quasi-diagonality things, and not going into this. Yeah, so this is what I wanted to say.